Hey everyone, and welcome to the Deep Dive. Today, we're going deep into the math that's making this whole AI thing tick.
It's wild, right? All this math we might have thought was just theoretical.
Yeah.
It's actually powering these AI systems that are doing some pretty mind-blowing things.
Totally. We've got two sources to help us unpack this. One's a deep dive on the specific math behind AI and machine learning.
And the other traces this whole history of how computers and math have evolved together leading up to modern AI.
Yeah, I'm super curious to see how it all connects, that whole historical angle. But first, can you give us a breakdown of the math we absolutely need to grasp if we want to understand AI? What are the essentials?
Let's start with linear algebra. People might remember it from school, all those equations and matrices, but it's how AI systems represent and process data, especially with things like image recognition.
So that's how those AI apps can tell what's in a picture. Like, it's not magic, it's linear algebra.
Exactly. Then there's calculus, which is where things get really interesting. Calculus is the engine behind how AI actually learns. One key concept is gradient descent, which is how AI systems find the best solution to a problem. They keep adjusting their parameters, like trying different approaches.
So they're constantly experimenting and learning from what works and what doesn't, getting closer and closer to the optimal solution.
Yeah, that's a great way to put it. And this gradient descent thing, it was huge because it allowed us to train AI on these massive data sets, leading to all these breakthroughs we're seeing now, things like natural language processing and computer vision.
So calculus is basically the engine of AI learning. Got it. What else?
Next up is probability and statistics, all about uncertainty, predictions, understanding patterns in data, which are all super important for AI. Think of how music streaming services recommend songs you might like.
Right. They always seem to know my taste so well. It's kind of creepy, but also cool.
Yeah, it's probability at work.
Mm.
Then we have information theory. This one's a bit less well known, but it's super important for AI because it's all about quantifying information.
Quantifying information. Break that down for me. What does that actually mean in the context of AI?
It's like, how do we measure the amount of information in something, a message, or a data set? Information theory helps us understand this, and it's key for things like data compression, error correction, even understanding language. Like in natural language processing, it helps AI figure out which words are most important in a sentence so it can understand the meaning.
So it's helping AI sift through all the noise to find the signal, what really matters.
Exactly. And last but not least, we have optimization theory. This is all about finding the best solution to a problem, which is basically what AI is trying to do all the time.
So AI is like this ultimate optimizer,
Hmm,
constantly searching for the most efficient way to reach its goal.
exactly. And optimization theory provides the math tools to make that happen. It's especially important with huge amounts of data, which is what AI is all about these days.
Okay, so we've got linear algebra, calculus, probability, statistics, information theory, and optimization theory. Those are like the pillars of AI, right?
It's pretty much.
But AI didn't just appear out of nowhere. It's been a journey.
You got it. And that journey is totally intertwined with how computers themselves have evolved.
Right. And our second source dives into that, taking us back to the mid-20th century when the foundations of modern computing were being laid.
Exactly. And a big name in that story is John von Neumann. He came up with the von Neumann architecture back in 1945. It was revolutionary because it proposed this way for computers to store both data and instructions in the same memory location.
I vaguely remember that from a computer science class,
Yeah.
but I never really got why it was such a big deal. Can you explain it in a way that makes sense, even if you're not a computer whiz?
Think of your smartphone. It has a processor, the brain, and memory, where everything's stored right. In the von Neumann architecture, the instructions for what the processor should do and the data it needs are both in the same memory space. This makes processing way faster and more efficient compared to older systems where things were stored separately.
Ah, so everything's in one place, no need to go back and forth.
Exactly. And that simple idea really changed the game. It paved the way for more complex, powerful computers.
So an idea from the 1940s is still relevant to the phone in my pocket. That's mind-blowing.
It really shows how foundational his work was. But of course, the story doesn't end there. The invention of the transistor in 1947 was another huge moment. They replaced those big, clinky vacuum tubes that were in early computers.
So transistors made computers smaller, faster, more efficient.
Exactly. They led to integrated circuits, or ICs, in the 50s and 60s, which were whole circuits on a single chip with thousands or even millions of transistors.
Wow, so we went from room-sized computers to devices we can hold in our hands.
Yep. And this miniaturization continued with the microprocessor in the 70s, which is basically the CPU of a computer. That's what made personal computers possible.
Right, the PC revolution. I remember when computers started showing up everywhere, like a whole new world.
It was a huge shift, and all these advancements were driven by this push to make computers smaller, faster, more powerful.
It's amazing how it all fits together, from the von Neumann architecture to transistors to ICs to microprocessors. This whole journey of innovation and miniaturization.
And it all happened because of this close relationship between computer science and math. Every step of the way, math was crucial for designing, building, and improving these machines.
So math wasn't just some side note, it was driving these technological revolutions.
Exactly. And that brings us to another big milestone, the birth of the internet.
Right, the internet changed everything. How we communicate, access information, live our lives.
For sure. It started as ARPANET, this network developed back in the 60s and 70s, but it eventually grew into this global network of computers we know as the internet.
Yeah, it's hard to imagine life without it now. It's woven into everything we do.
And it's created this massive amount of data, which is what's fueled the AI revolution.
Okay, so we've gone from the von Neumann architecture to the internet. It's mind-blowing how all these developments came together to create the tech world we have today.
It's a pretty wild story, and it shows how seemingly small advances can have these huge ripple effects that change the world over time.
Totally. But I'm curious about how we went from those early computers and the internet to the sophisticated AI we have now. What role did math play in that transition?
That's a great question, and that's what we'll dig into in the next part of our deep dive.
Okay, I'm hooked. Let's take a short break, and then we'll explore the modern era of AI and how math is shaping the future. Welcome back to the deep dive. Before the break, we were going through this incredible evolution of computers and math, and I'm dying to hear how we actually got from those early breakthroughs to the super sophisticated AI we see all around us now.
Yeah, it is quite a leap, right, from those early days to now. And what's fascinating is how all those math fundamentals we talked about earlier are a huge part of making it all work.
Okay, so connect the dots for us. How did we go from the internet and this explosion of data to the AI revolution?
Well, remember all that talk about big data and this massive amount of information available online. That's a key ingredient here. We had all this data, but then we needed new math tools to actually make sense of it all, and that's where things like probability, statistics, and optimization theory became so essential.
So it's like the internet gave us the raw ingredients, and then math gave us the tools to turn those ingredients into something amazing, something meaningful.
Exactly. Imagine you have this huge block of marble. That's your big data. But you need the right tools, the math tools, to sculpt that marble into something beautiful. And in this case, the beautiful thing is your AI system.
Love that analogy. I can really see how all these pieces fit together. But what about the actual AI algorithms themselves? How have they evolved?
One of the biggest game changers in the past few decades has been deep learning. These algorithms are inspired by the structure of the human brain, actually. They use these things called artificial neural networks to analyze and learn from just huge mountains of data.
I've heard a lot about neural networks, but to be honest, they've always seemed kind of mysterious to me, like a
Right.
black box. Can you break it down, explain it in a way that anyone can understand?
Sure, think of it like a web, a network of all these interconnected nodes.
Yeah.
Each connection between those nodes has a certain weight, which represents how strong that connection is. As the network learns from data, those weights get adjusted. It's like fine-tuning, and this lets it make more accurate predictions and decisions over time.
So the AI is constantly refining its connections, like strengthening some, weakening others, based on what it's learning, kind of like how our brains make new connections as we learn.
Exactly, and that ability to learn from data is what makes deep learning so powerful. For example, in image recognition, a deep learning algorithm can be trained on millions of images. And through that training, it learns to spot those patterns and features that allow it to distinguish, say, a cat from a dog, or even tell different faces apart.
That's crazy. So the more data you feed these algorithms, the better they get at recognizing patterns and making predictions.
Precisely. And that's another reason why having all this big data has been such a catalyst for the AI revolution. But it's not just about the volume of data, it's also about having the right mathematical tools to process and analyze it efficiently.
Right, it always comes back to the math. So let's revisit some of those key mathematical areas we talked about before and see how they're actually put to use in real-world AI.
Okay, let's start with linear algebra. Remember we said it's basically the language AI uses to see the world. In image recognition, each image gets represented as a matrix. It's like a grid of numbers representing the pixel values.
Oh, so it's like turning a picture into a giant spreadsheet.
Exactly. And linear algebra gives us the tools to work with those matrices, to analyze them, and that allows AI systems to identify patterns, edges, shapes within the image. It's how facial recognition software works, for instance.
So linear algebra is the reason AI can actually see and understand images. Wow. What about calculus then? Where does that come in?
Remember that gradient descent thing, the algorithm that helps AI learn by minimizing errors? Well, gradient descent is based on calculus. It uses these things called derivatives, which are a way to measure how a function changes to figure out which direction will lead to the smallest error.
So calculus is like the engine that drives the learning process, always guiding the AI toward the best solution.
You got it. Think of it this way. Imagine you're climbing down a mountain, but it's super foggy and you can't see the path. You can feel the slope of the ground beneath your feet, though, right? Gradient descent is kind of like using that slope info to guide your steps, leading you down the mountain to the lowest point one step at a time.
That makes it so much clearer. Great visualization. Okay, so how about probability and statistics then? How do they fit into AI?
Okay, think of a spam filter, something we probably all use every day. A spam filter uses probability to figure out how likely it is that an email is spam. It looks at things like who sent it, words in the subject line, the actual content of the message.
So the AI is weighing all these different factors
Yeah.
and using probability to make a smart guess, essentially, about whether it's legit or spam.
Exactly. And it gets better at making those guesses over time as it sees more data as it learns.
That makes sense. So what about information theory then? How does that come into play?
Information theory is really important for natural language processing. That's where AI has to make sense of human language, which can be messy. One key idea in information theory is entropy, which is a measure of how uncertain or random a message is.
So a message that's really random and unpredictable has higher entropy.
Exactly. And AI uses this idea of entropy to analyze text, to pick out patterns and figure out what it all means. For example, those machine translation algorithms, the ones that translate languages, they can use information theory to determine the most likely translation of a sentence, looking at the context of the words and the overall meaning of the text.
So it's helping AI deal with all the nuances of human language.
Right, because it's not always straightforward. And then we have optimization theory. Remember we said AI is this master optimizer? Well, optimization theory gives us the mathematical tools to find the absolute best solution to a problem, even when there are a zillion possible solutions.
Can you give me an example of that? How optimization is actually used?
Sure, let's say you're training a deep learning model to recognize handwritten digits. You have to adjust millions of parameters in the neural network to get it to work well, to get the best accuracy. Optimization algorithms help find the ideal values for those parameters so the model can recognize those digits accurately.
It's like fine-tuning a super complex machine, making sure everything is working in perfect sync.
Exactly. Optimization theory makes AI systems efficient and effective.
This is really fascinating stuff. It's amazing how all this math, things that might have seemed abstract back in school, are actually being used to create these incredible technologies, these AI systems.
It is pretty remarkable. It shows how powerful math is in shaping the world we live in. But it's important to remember that the AI story is far from over. We've got a long way to go, still lots of challenges ahead, and we're going to need new mathematical breakthroughs to overcome those and unlock the full potential of AI.
That's a really great point. So what's next for AI? What trends and challenges should we be keeping an eye on?
That's the perfect lead-in to the last part of our deep dive, where we'll explore the future of AI and what it means for all of us.
We're back for the final part of our deep dive into the math powering AI. We've covered so much ground, the math, the history. It's been amazing. But what about the future? What's next? I'm really curious to hear your thoughts on that.
Oh, the future of AI is just brimming with possibilities. One of the most exciting things is seeing how AI is starting to actually make a real difference in people's lives.
Okay, let's start with the positive stuff then. Where do you see AI having the biggest positive impact?
Healthcare is huge. Imagine AI systems that can look at medical images like x-rays and scans and spot things like cancer super early when treatment is much more effective.
That would be incredible. A total game changer for so many people. What about other areas? Where else is AI poised to make a difference?
Education is another one. AI could personalize learning, tailoring lessons to how each student learns best. It could give instant feedback, helping students figure out what they need to work on.
So it's like having a personalized tutor for every student. That's amazing.
Exactly. And it could make education accessible to so many more people around the world, no matter where they live or their background. The possibilities are really exciting.
It does sound like AI has the potential to make our lives healthier, easier, and more fulfilling in so many ways. But of course, there are concerns too, right? What about the potential downsides of AI? What are some of the challenges we need to be thinking about?
One of the biggest ones is job displacement. As AI gets smarter, it's going to be able to automate a lot of tasks that humans currently do.
Right. A lot of people are worried about losing their jobs to robots, essentially.
It's a legitimate concern, and it's something we need to be proactive about. Investing in education and training so people can learn the skills they'll need for the jobs of the future. We need to think about how to prepare the workforce for a world where AI is more and more integrated into everything.
So it's all about adapting, right? What other challenges are there?
The ethics of AI are huge. As AI systems become more autonomous, as they're making more decisions that affect our lives, we have to ensure they're aligned with human values and that they don't reinforce harmful biases.
Yeah, we want AI that's actually beneficial, not something that causes more problems.
Exactly. And it's an ongoing discussion, one that involves everyone, researchers, policymakers, the public. We need to really think about fairness, transparency, accountability in these AI systems.
It's not just about the technology, it's about how we use it.
Exactly. And that brings me to another challenge, which is explainability. As AI systems get more and more complex, it can be really hard to understand how they're making decisions.
So we want AI we can trust, but we also need to understand how it works.
Right. Imagine a medical AI that can diagnose diseases, but we have no idea how it's coming to those conclusions. That's a tough one. So there's a lot of work being done on making AI more transparent, more explainable.
It sounds like the future of AI is this mix of incredible opportunities, but also some really tough challenges.
That's a perfect way to put it. It's exciting, but it's also a little daunting. But overall, I'm optimistic that we can work through those challenges and harness the power of AI for good.
I am too. And this deep dive has been so helpful. I feel like I have a much better grasp on what AI is, how it works, and where it might be going.
I'm glad to hear that. And I think it's important to remember that at the core of it all is this relationship between math and AI.
Right. Math is like the language that lets us understand and shape this technology that's changing everything.
Exactly. So whether you're a student, a professional, or just curious about AI, I encourage you to really embrace the beauty and power of math. It's the key to unlocking the secrets of AI and shaping its future.
That's a fantastic message. Embrace the power of math, everyone. And thank you all for joining us for this deep dive into the math that's powering AI. We hope you enjoyed it.
It's been a pleasure exploring this with you.
This is The Deep Dive, signing off.